This module is on how to solve equations, especially with data science applications. We need to solve them. They're the root of almost everything we do in data science, in turning data into some type of model or actionable information. So let's just consider an equation that we have. For example, y equals a x squared plus bx plus c. This is one that many of you are probably really familiar with. You can solve this, the roots of it, if y equals 0, you could solve for x is going to be negative b plus or minus square root b squared minus 4ac divided by 2a. Okay, so we know how to solve that. So let's just say we had multiple equations that we can't necessarily find an analytical solution to. We might need to use a numeric solution where the solution of that is determined by computer algorithms that are able to rapidly test many different solutions and figure out when that equals 0. Another way to solve these, particularly in Python, that we're going to be focusing on is a symbolic solution. So for simple ones, we're going to be using a package called SymPy, and in numeric we're going to use a package, we're going to use fsolve that's in that is part of the SciPy package, or we can use Gecko as well to solve equations. So a couple different options for numerically solving them, and then at least one option for symbolic solution. Okay, so let's just talk about numeric solutions. We're going to use the SciPy optimize fsolve. So the thing to consider here is we have a function that we've declared. The thing that we're returning from the function, that has to equal 0. But there are two solutions to this. If you solve the quadratic formula, you're going to come up with these two solutions. Now numeric solutions, it depends on where you start. So if I start from 0 and 1, they're both going to finish up closer to the root that they started from. But if I start somewhere like -5, then it finishes at the root that's closer to the starting point. Okay, so numeric solutions typically only return one solution, and they're often not precise, so you can see all of the decimal points, and this is going to be accurate maybe to machine precision. Okay, so that's fsolve. That solves a series of equations. You can also solve it with something like Gecko, where you declare a variable y and you declare your equation and then you solve it. Okay, and then you can solve it again with a y value is -2, and then just solve it again and print the value. Okay, same solution that's obtained. Okay, the equations, when there's two equations instead of one now, for large sets there may not be an analytical solution. For simple sets there may be. Okay, so we're going to solve this. I just added an additional equation and put y here instead of 0, and then x equals y, and then we solve those two together. The thing that we need to return is one equation, everything on one side of the equation. So I put a negative here in front of these, and then solved it again. And actually this needs to be a negative right here. Okay, so it looks like it wasn't able to solve that, so I might just go back in here and change this problem. Sometimes there's no solution to them, so I'm just going to make it so there is a solution, so there's no imaginary numbers. Okay, so let me I'll just fix that one later. Okay. Alright, so let's go on to the one with Gecko. Okay, we're going to try to solve this with Gecko, and it came up with a similar or the same result here. Now in this case I just put the variables and equations on either side of the double equal sign, and that makes it so that we can it's a little bit easier to read. You don't have to put it all on one side of the equation or the other. Alright, and then I replace it with different starting values of -2, and then you can see that it came up with the solution here as the same as before. Okay, so let's solve some equations. Let's go ahead and just try this one. This one is a series of a couple equations. An additional one, this is going to be 3 equations, 3 unknowns. And let's start with the SciPy optimize fsolve. So the very first thing we need to do is just create a new function. I'm going to make that a function of a, and just say it's x, y, and z. I'm going to split those out, and then I'll return the list of the equations. So equation 1, equation 2, equation 3. Okay, I can do it that way, or I can fill it in here, and I'm just going to put in x squared plus y squared plus z squared minus 1. I've got to move it over to the other side of the equation, so it's all on one side, and x minus 2 times y plus 3 times z, and minus 0.5. Alright, and then x plus y plus z. Alright, so if I just say, let's go ahead and print f of, let's go ahead and put in 3 values, 1, 2, 3. Then let's see, 1 positional argument, but 3 were given. Alright, so let's go ahead and just make that a list that we input. Okay, and then it's going to return a list of the results. So we know we've satisfied these equations when all of these are 0. So let's just try that now with fsolve. We're going to solve this and return x, y, and z, which are solutions. And we'll say fsolve. We need to give it the function name and then some guess values. Okay, we'll just guess 1s for all of those. If you want a shorter way to do it, you can say 1 times 3. Okay, and then we need to print x, y, and z, and there are the solutions. Or we can just print the result of fsolve. Okay, it gives the same result. Alright, let's do this with Gecko as well. Just another package for solving equations, but also for optimization and some other capabilities as well. I'm going to say m equals Gecko, and then I'll define x, y, and z as an array. I'll use the Gecko array function and say that's going to be variables, dimension 3, and I'll give them an initial guess of 2. Alright, and then let's do the equations, and I'm going to just borrow these from up here. They're going to be similar, and put in an array. I'll just put it on either side of the equation. Okay, I'll put the double equal sign here and double equal sign 0. Alright, I have my equations set up. Now I'll go ahead and solve it, and I won't display the solver output, and then I'll finally go ahead and print. I can do x, y, and z. Okay, those are just going to be the Gecko variables. So what I need to do here is dot value, dot value, dot value. Okay, and it gave the same solution as up here. Okay, let's go on to symbolic solutions now. So symbolic solutions are nice because you can, for simple problems, you can get an analytical solution. So for example, for this one, it's going to solve basically the quadratic equation. It recognized that it could solve it and returned it symbolically in terms of exact answers. Square root of 17 in here, so minus 1/2 plus, or okay, and you have plus or minus, okay, and then you have the other solution right here. So negative 1/2 plus or minus square root of 17 over 2. All right, so let's go ahead and just solve these 3 equations symbolically now. We want to do this with SymPy instead of instead of something else. Okay, so I'm going to let's see, x, y, and z. Let's see if those are already defined. I can do it this way right here. Kind of a shorter way to do that is go from SymPy dot ABC import and then x, y, z. So you can get your symbolic variables that way. Okay, and then answer equals sim dot non-lin solve, and this is going to be x times y times z, and then our next one is x times y, and then x plus 5 times y plus z. Alright, we need to tell it which variables to solve for, and so I'm going to put x, y, and z, and then I'll display the answer. And to get the nice display, we need to just import from IPython display import display. Alright, so you'll see that this solution is interesting because it has z in the solution. So this one is equal to, basically it's underspecified, and so it has an additional degree of freedom, which is z, and it recognized that and then gave the solution in terms of z. Alright, let's go on to the next one, linear equations. So we're going to use just linear algebra to solve something like ax equals b, and there's a couple different ways to solve this. Ax equals b, we can multiply both sides by a inverse. Alright, and then this, we could take the inverse of that, and I have to erase this side again. Okay, I'm going to multiply both sides of the equation by a inverse times a, and then the inverse, and then I have a inverse times x. So I can solve it this way, times b. Let me put b back in there. I could solve it this way if I want. Okay, and take a inverse and multiply these matrices together. This is an inefficient way of solving it. There's a more efficient way, which is the NP-linalg, and we're going to use the solve, where we put in the a and the b, and then it's going to use a method to solve this system of equations, ax equals b, and it'll do that efficiently. We just need to put in the a value and the b value, and then it's going to solve for x. Alright, and so if I just define the a and the b and plug those in, it's going to solve it for me for this x value. Okay, we can also do the same one symbolically, or get an exact solution here, so you can see it does it in terms of the fractions. Okay, so equations, when there are more variables in equations, we can't use a package like fsolve. We have to use optimization software, and one of those is again in the SciPy package. This one's going to be in the SciPy optimize, and we're going to use the minimize function. Now, in order to use that, we need to define an objective function, something that will return the objective, and then any constraints that we might have as well. So the problem that we're solving is this. Here's our objective function. We're subject to this inequality constraint. We have an equality constraint here, and then some upper and lower bounds on x1 through x4 that they have to be between 1 and 5. We also give it this initial guess right here. Alright, and so here you can see all of the equations, inequality, inequality, and we are going to define a new inequality constraint and a new equality constraint, and then when we minimize, we give it this objective function with our initial guess, and then our method that we want to use, some of the bounds. Okay, the bounds are going to be between 1 and 5, and then the constraints as well. Alright, and this solves it, and then you can print out the solution. Okay, it's fairly fast. Here's the solution. Now the SciPy optimize minimize optimizer is an okay solver for problems with few variables, But if you have something that's larger, then you want to use a different tool. One of those is Gecko, and this is similar. It sets up the variables, gives some initial values, you set up your equations, your objective function, and this could be either OBJ, or you could do minimize or maximize, and then you solve it and then print out the final objective and the solution. Okay, so there is the solution with Gecko. Alright, let's get on to the TC Lab application. Now this one, we are going to generate some data, and then we're going to solve a couple problems similar to the ones that we just learned about. So let's first of all just import a few packages. I'm going to need TC Lab time, and then also I'll import NumPy as MP. I think I may have imported that one already. Okay, and I'm just going to say n equals 19. And I need to turn on the heater 1 to 100% and record T1 every 10 seconds for 3 minutes. So let's just define our time first of all. Linspace, and we're going to go 0 to 180 with 19 points. So that's going to be a 10-second interval. And then T1 is blank and T2 is blank. And then we'll put values in there as we go along. As lab, okay, so I'm going to connect to the TC Lab and then put in the 100% for heater 1. And then for I in range, and we're going to use up to n, which is 19. And then every time through this, we're just going to append, and we'll append lab.t1, and then we'll also append to t2. Alright, and now let's just go ahead and print that just to see what's happening during these 3 minutes. And we'll do T2 as well. Alright, so there is our printing, and then we'll have to sleep for 10 seconds. Alright, the very first final thing that we'll need to do is just make a note of what happened at 0, 90, and 180 seconds. We're going to need just those points for some of the analysis we're going to do later. So that's going to be time at 0, 9, and let's see, this is going to be 19, the very last one. Alright, and let me copy this, and then I'll also do that for T1 and for T2. T1 and T2, T1 and T2. Okay, I'll get this one started just so you can get through this fairly quickly. Alright, and then let's look at our problem as we're generating this data. So 3 points are required to specify a quadratic polynomial. We have y equals a function of x, and so we want to create a quadratic regression of T2 by only using the first, middle, and last data points. So it's 0, 90, and 180. So let's just say we were given these, and to solve this, we're going to plug in those points, the time for x and the temperature for y. We'll plug that in 3 different times, and we'll have 3 equations and 3 unknowns, which are the coefficients a0, a1, and a2. Okay, and this is going to be in matrix form. It's going to look like this, and so we want to solve this as an ax equals b problem. Let me just come up with our matrix M, and this is going to be np dot array, and let's go ahead and put in our values here that we see, and then we'll have to come up with our temperatures in just a little bit after they finish with that problem, okay, with collecting it. Alright, 180 squared. Alright, so here is my M, and I'll have my B. I'm not using A there because I have the lowercase a. It might be just a little bit confusing. And I'll have T2, and I'll put in 0, T2 9 and T2, and this is going to be 19. Okay, let's solve this for the A coefficients. And so I'm going to say that A is going to be equal to, and np dot lin algebra dot solve, and I'll just put in the M and the B. Okay, and then we want to plot this once it's done. So this is going to give us the coefficients that we want to be able to plot. I'm just going to do all of the times in T2, and let's make those red dots. And then let's plug in now. Let's do the time. Let's see, we just need, I'm trying to think how this is going to work. Okay, np polyval, let's try this, and let's put in the A coefficients, and then we need the times in there. So this is going to help us predict what is the value of that polynomial that we're fitting over this time. So let's just see how far it is along. You can see the data point that we have here, and it looks like somehow the heater was not on or going at the time. I might need to rerun this again. I'll just go ahead and pause the video, or we can start working on the final problem and then go back and redo this one in a second. Okay, so, oh, and I did have an error here as well. That should be 18 instead of 19. Okay, because it only has a dimension of 19. Okay, so there we have a corrected version of that. And I'll just start that again. Let's start working on the last one down here. I'll correct this one as well. Instead of 19, we'll say that's 18. Okay, we'll solve this one in just a second after it finishes. Okay, similar to the last one, the linear one, we're going to solve a set of nonlinear equations. And we're going to just plug in, similar to what we did with the linear, but now this is a nonlinear expression. And let's say we had 22, 42, and 52, then here they are. Here are the values that we're going to have in the 3 equations and 3 unknowns. So let's go ahead and solve this similar to how we did it before, but this in this case it's going to be with this is nonlinear, so we're going to have to use fsolve to solve this. Okay, so here we have okay, let's see, this is going to be fsolve. We need to define our function f of z, and f of z is going to be a, b, and c, and we're going to split that out from z. So we're going to go ahead and just expand those, and then I need to return in this case it's going to be the expression ti t1i, okay, and minus a minus b times np exp, and then c times time I. Alright, and then I can return the whole list of this. I don't have to write that out many times. I can just use a list comprehension for I in 0, 9, and 18. Alright, and that's going to return the values plugged in for 0, 9, and 18, and I'll need those for evaluating my expression. And so A, B, and C are going to be fsolve, and that's going to be f. And then I'm going to have here, I'm going to give it some initial guesses. And so let me just say 1, 1, and 1, and then see if that's able to solve it for me. Okay, and that will run after after this finishes in 3 minutes. Let's just see how it's doing with collecting the data. It looks like we have just 2 more samples left, and then we'll try to solve this one and also the linear equation one for these 3 coefficients. Okay, almost done, and there it goes. Okay, so it's just going to say TC Lab disconnected once it's finished. Alright, and then if I come down here and solve this one again, alright, and then print A, B, and C, okay, you can see some of the values that it came up with. Alright, so I had T1, let's just see if I did this right. Okay, so first, second, and third values, and okay, so it did heat up quite a bit on T1. T2 heated up just a little bit. All right, I'm going to go ahead and do this. Okay, so it says only 2 non-keyword arguments are accepted. Okay, so I think I just forgot the final enclosing brackets here. Okay, and PLT is not defined, so let me go import matplotlib.pyplot as PLT, and then do matplotlib inline. Okay, so that does not look quite right. Okay, so it should go through the different polynomial points here. But something is not quite right with the solution here. So let's just check these. Okay, those look correct. These look correct, and those look correct as well. I have the B values. Oh, I think I know what happened. We need to flip them around. So I need to take these A values, and I need to do numpy flip, and let's see if that fixes our problem. Okay, it did. So it goes through this point, the middle point, and then the end point. So we just needed the 3 points to help us define the fit and define those 3 coefficients for us. Okay, so I just had to flip the order around. The very first one and the third one just need to be swapped. All right, so there's our linear one. Let's go on to the nonlinear one and just see if we can create a plot here and just see how well this one is going to fit. All right, I'm going to just create a plot, plt.plot, and I'll do time in T1. And let's put in red circles, and then in this case, plt.plot, tm, I need the model prediction. So I'll do a plus b times numpy exp, c times tmi. All right, and then let's see, what else do I need? For I in, and then I'll put 0, 9, and 18. All right, and let's go ahead and make this a black dashed line. And let's see, I have an error here. Let's just look at this error. They must have the same dimensions. Okay, so let's do all 19. I don't think we need to just do these for I in range, and I'll just put n here. Okay, so you can see it, it didn't really converge, didn't give a good solution here. So I'm going to get something that's closer to the correct solution. One of the things you'll notice with fsolve is sometimes you've got to give it a close solution for it to converge. and you can see even here it isn't making good progress. Okay, so let's see, I'm going to try to get something. Still didn't do it. Okay, so yeah, this one, you got to kind of work with it. Let's see, nope, still didn't come up with a good solution. So let's try something like, I'm going to just insert a cell below. Let's try Gecko instead and just see if Gecko can solve this one. All right, and I'm just going to replace this with m equals Gecko, and then remote equals false, and then we'll do A, B, and C. Those are the ones that we're going to try to solve for. And this is going to be an array of variables, size 3, and we'll give it a value of 0.1. And then let's just say that our equation equals, and we'll do another list comprehension here. Okay, and I'll do equations here, and T1I equals, and then I'm just going to copy what I had before, but I'm just going to put some positive signs here and replace just one thing in this equation. Okay, so I'm going to just borrow it right here, and I'm going to say equals A, and then put a plus sign here for B, and replace this numpy with the Gecko version of the exponential, and then this one is for I in 0, 9, and 18. Okay, and I think that sets the equations. Now let's go ahead and just solve it, and we'll just say display equals false, and then we'll print a dot value, b dot value, and c dot value. All right, and let's see what this says. Here are the values that it came up with. Okay, and then there's just a problem with the plot. All right, oh, I think I know what that is. I just need to, I'll just say a equals a dot value, b equals b dot value. Okay, just to extract the values from these. C equals c dot value. Okay, so you can see it gave a good solution. It visited this point, and this point, and the other ones actually fit pretty well as well. So I can go back into SciPy now and maybe replace the solution I got from Gecko into SciPy and see if I can get something a little bit closer. So I'm going to basically tell SciPy what the answer is and just see if it gets the same solution, if it can start with something just a little bit closer. So it looks like SciPy did finally get it, or the fsolve, but I had to give it something a little bit closer, and so if I just replace this with 100 and then maybe minus 100 and then something like this, that should also be able to get it. Okay, so something closer, you know, fsolve needed something just a little bit better, whereas Gecko is able to handle a worse initial condition and be able to find the answer to this problem. Okay, so that's it for equation solving. I'm just going to review what we've covered so far. We had just a single equation, and it showed how you can give different initial guesses to get different local solutions. Showed fsolve and also Gecko, and then moving on to 2 equations or more. And we did a a practice example there with 3 equations. And then also covering some symbolic solutions as well. And, with multiple equations, and then linear equations as well, which is just our separate, if they are linear, they're more efficient methods to solve those than things like fsolve. And then we also covered a little bit about optimization. And then with the TC lab, we collected some data and then solved sets of 3 linear or nonlinear equations.